Well, so I'm happy to present a recent work with Alemivdawi and Jean Ludovic on worst-case data bounds in time-sensitive networks with packet replication and elimination. And apparently, I was so happy that I was the first one to register, which is why I will be the first one also to talk about time-sensitive networks, but probably many presentations will do the same. And time-sensitive networks, as in the context of IEEE TSN, they aim to provide basically an Ethernet for safety-critical applications. And to do so, they cannot only provide the classic bus-to-4 service that we find on classic Ethernet, but instead they provide 4 key components of TSN that are bundle latency with guarantee of no loss by congestion, high levels of reliability, time synchronization, and resource management. And we find the same ideas at layer 3, so in DetNet, which is the working group of the IETF. And of course, in my presentation, the focus here will be on the service of bundle latency and how to achieve this bundle latency. So the working groups to achieve bundle latency, they have developed several mechanisms, including class-based queuing mechanisms, in which the access to the resource, so the transmission link, is shared between classes up to 8. And just I want to mention very briefly that in TSN, the access policy is made of 2 stages. There is an asynchronous stage with asynchronous schedulers such as click-based shaper, and a time trigger gate stage with a global scheduler. This, I will simply call it the class-based queuing system. And the way we analyze this type of network usually is by analyzing n FIFO network, 1 per class, in which I simply view my system here. Oh, sorry, I need maybe for Zoom to do it this way, in which I view my system here as a service curve element that is FIFO for the flows of my class, and that provides the beta in purple, the leftover service curve for this class. And then since we have several in the network, we use compositional approaches to compute end-to-end latency bands, such as total analysis, multiplexing only once, linear programming. There is another set of mechanisms in TSN that are per flow traffic regulators, and they allow for per flow control, because when my flow here, F1, enters the CBQS here, it still competes with the other flows from the same class. And so its arrival curve, its burstiness will increase at the output. And this can lead to issues in network with cyclic dependencies, most notably. So for example, we can place a per flow regulator that will reshape the flow back to its original profile. So it's a queuing element, it stores the packet in order, and then it releases the head of line packet only when doing so does not violate the shaping constraints. And so thanks to this, I control the per flow arrival curve here. But of course, this is a queuing element, so we need to account for its delay. But we have an essential property in which if the previous system was FIFO per flow, then the per flow regulator has not increased the worst case latency bounds. And this is called the shaping for free property. Of course, with the per flow regulator, if I want to shape another flow, I will use a second one, which is why in TSN, they use a different mechanism that is called so asynchronous traffic shaping in TSN, but also interleaved regulator, in which all the several flows that share the same previous system share also the same FIFO queue. They each still has its own regulation parameter, but the interleaved regulator looks only at the head of line packets and releases it as soon as doing so does not violate the shaping constraint for the associated flow. But the following packets are blocked by this head of line packets. Still, we also have the shaping for free property of the interleaved regulator. This time it requires the previous system to be FIFO for the aggregate and not anymore FIFO per flow. So in TSN, we have, as I said, class-based queuing mechanisms and traffic regulators to provide bundle latency. But this is not the only service offered by TSN. As I mentioned, there are 4 services. We analyze their effect using network calculus. But the other service is high levels of reliability. And this is provided through redundancy mechanisms. They have several names. In TSN, this is called frame replication elimination for redundancy. In DetNet, this is called packet replication elimination ordering functions, or pre-off, and I will use the second terminology. So the idea, of course, is very simple. If I have a flow and this is its path, if the reliability of C is not sufficient to ensure the end-to-end reliability of my flow F, then I will simply use a redundant path parallel to C. And then at the level of a packet, when my source sends a packet, I will simply call data unit the content of this packet. And when it arrives in B, there is a packet replication function. In TSM, this is also called the stream splitting function that sends this data unit into two new packets, so the green one here and the blue one. And then when the packets arrive, if they are not lost at F, then a packet elimination function will remove the duplicate, so the second one. And here I'm assuming the blue one arrives after, so it is the second one. And only the first one will be forwarded to the destination. So the packet elimination function is also called the sequence recovery function in TSN, but this is very misleading. As we will see, the correct sequence of packet is not recovered at the end of the packet elimination function. And so we have these two sets of mechanisms. And my main concern here today is, do these mechanisms, the redundancy mechanisms, have side effects on the primary objective of bounded latency? And do they interact also with some of the bounded delay mechanisms here? So to analyze redundancy, we first have the packet replication function. It is very easy to analyze because it's performed by the switching fabric. This is a mechanism similar to multicast. And so any input arrival curve is a valid arrival curve at the output for each subpass. However, the packet elimination function is a specific function located in the output port just before the CBQS. And to compute a latency band through the CBQS and in the downstream node, I will require an arrival curve for my flow at the output of the packet elimination function. And obtaining this arrival curve is the main challenge of analyzing the effect of redundancy mechanisms on latency bands. Here, I will assume the packet elimination function is correctly configured. It drops all duplicates and only them. So in TSN, this is performed with several algorithms with parameters. So I'm going to assume that the parameters are correctly configured. And there is a recent paper from Lisa Milo et al. That, among other results, provide the results to correctly configure the parameters in TSN. But here, I'm simply going to assume it's correctly configured, and I'm interested in an arrival curve here at the output. So what can be the shape of the arrival curve at the output of the packet elimination function? For this, I'm using an example. So flow exit B, then we have a packet replication function. It is sent through C with these latencies between 0 and 1, and D between 6 and 7. Then the path merge, and the packet elimination function removes the duplicate. I will assume a periodic arrival at the input, and I'm going simply to assume that the first packet is lost inside C, and it is received through D with a latency of 7 time unit here. I do the same for all the following packets, including packet 6. It is lost inside D and received only through D, inside C and received only through D. And then, starting at packet 7, I assume both paths are available again, and my packets, my data unit 7 is received through both paths. So here with a latency of 1 through C and 7 through D. And I do the same for all the following. Then the packet elimination function receives the sum of the two and removes the duplicates. The duplicates here are these two packets, sorry, because 7 and 8 have been received already. So the output looks like this, and we observe that it is bursty and out of order. And so our first question would be, the output is bursty and misordered. Can we bound this misordering and this burstiness? And as I've said, I will require a bound on this burstiness to be able to compute latency bounds in downstream nodes. But even if we obtain a bound on this burstiness, it can be high, and so it can lead to high latency bounds in downstream nodes. So perhaps here there is the opportunity to use our traffic regulators that allow for a per flow control to reshape the flows. So on the first topic, in the paper that we have published, we provide the theorem of the output arrival curve at the output of the packet elimination function, and it has several items. The first one is that if I achieve to obtain an arrival curve at the input of the packet elimination function, then this is also an arrival curve at the output. And this, I will call it the intuitive approach, because it assumes basically that the packet elimination function never removes any packet. In addition to this item, I can also consider what I call diamond ancestors. So these are the nodes that are located in any path between the source and the packet elimination function. So here, any path between A and F contain both A and B. And so for any of those here, I can view this situation as this one, where I have my ancestor. Then I have a part of my network that is not assumed to be FIFO or lossless in general. But by analyzing each subpath, I can compute lower and upper bounds for the latency. And also, I assume I know the arrival curve at the output of the ancestor. And then knowing these two pieces of information, I can obtain a new arrival curve for the at the output of the packet elimination function. That is the arrival curve at the ancestor, mean plus deconvolution, the bounded delay curve of the jitter. So here delta D is a bounded delay curve that equals plus infinity after D. And my tight model would be to consider all of these in arrival curves by doing their mean plus convolution, because each item provides a valid arrival curve. So if we look at the application of the toy example, here I have an arrival curve at the ancestor gamma R0, B0. R0 is 1 packet every time unit, and B0 is 1 packet of burst. Then by analyzing each subpass, I can obtain the arrival curves at the output of C that are leaky buckets arrival curve with a rate R0 and a burst 2B0, and D as well. And simply my packet elimination function receives the sum of the two. So its input arrival curve is the leaky bucket arrival curve with twice the R0 and 4 times B0. And so by application of our first item, this is also an arrival curve at the output of the packet elimination function. And so we obtain this. But in addition, my node B here is also a diamond ancestor. So I can take the arrival curve and then mean plus deconvolution of the bounded delay curve, where here the jitter is 7 minus 0. And I obtain this other piece of arrival curve. And so the mean plus convolution of the two is an arrival curve for my flow at the output of the packet elimination function. And for this specific case, I can build a trajectory here for which, if I plot the cumulative arrival, I see that my arrival curve fits the cumulative function. So we have a tight result here. Also, the tight model, so considering all the arrival curves of the item of the theorem, provides a better end-to-end latency band than the intuitive approach. So this is an industrial use case. It's based on the Volvo car. We have 48 flows, 40 of which are redundant. And by the way, here we also have cyclic dependencies in the network. And here you see the latency bands obtained. So in blue with the intuitive approach of only the first item of the theorem. And we see that for 4 flows, it cannot conclude on their schedulability. Whereas if we analyze the network with the tight model, we see that all flows meet their deadline. So the tight model provides significantly better end-to-end latency bands in use cases. And so on the question of obtaining a band on this burstiness, we provide novel network calculus results to obtain this band. Also, we provide a band on the misorderings caused by packet replication and elimination functions using the metrics relationship published by Mohammadpour and Ludovic. And so on to our second question, we have obtained a band for the burstiness, but it can still be high in the and leads to high latency bands in the downstream nodes. So perhaps I can use a traffic regulator to reshape my flow. Where here, for example, I have a flow with an initial arrival curve, alpha phi. It enters the network with several redundant paths. Then it is processed by its packet elimination function. And here, as I've discussed, I can obtain an arrival curve at the output, but it will be larger than the initial arrival curve. So here, maybe I can place a per flow regulator to reshape the flow back to its original profile, and so obtain smaller latency bands in downstream nodes. Of course, the issue that I have now is that this previous system here is not anymore FIFO per flow, so I cannot apply the shaping for free property. And so in this case, we obtain a penalty, but that is bounded. And so the latency band through the concatenation is less than twice the latency band. So we can actually pay a penalty of using this per flow regulator that is equal to the latency band already suffered by the flow. And in some cases, we show that actually we can achieve this band. I know what happens if I consider an interleaved regulator. So here I have several flows that share the same previous network with redundant paths, and they have their packet elimination function. They are processed by the interleaved regulator that enforce their initial contract. And here as well, my system is not FIFO, the previous system. And this time we obtain a totally different result because we show that if the number of flows processed by the interleaved regulator is greater than a limit that depends on the properties of the network, then we can yield unbounded latencies. And for this result, I want to provide an intuition of the proof. Here I will consider 4 flows. So they have leaky buckets arrival curve. The rate is 1 packet every 7 time units. and the burst is 1 packet. They are sent to 2 paths, processed by their packet elimination function, and then we have the interleaved regulator that enforce their initial contract. Here I will highlight a trajectory that leads to unbounded latencies. And for example, focusing at the output of B, I will assume that my blue flow sends a packet here at 0, then the next one at 10, and then it restarts the same profile, but shifted by 24. And here you observe that the minimum distance is 10 between 2 packets, so this is compliant with my contract. I assume the same for the red flow, but simply it's shifted by 6. So it has exactly the same profile, but shifted. Then I will assume that here the blue A packet is lost inside C and received only through D with a latency of 6 time units here. And my B blue packet here is received only through C, so with a latency of 1, and lost inside D. I do the same for the red flow again. And here, our packet elimination functions, they receive the sum of the two, and they remove the duplicates. But here, as you can observe, there is no duplicate. So the output will be simply the sum of the two, which is this one. And here we observe the fundamental property of this trajectory. This blue B packet here and this red A packet here, they have exchanged their order. I had the opposite order previously. And this will cause instability, because when my interleaved regulator receives this profile, the first thing it needs to do is to postpone, to delay B, because it is too soon with respect to the A blue. And by doing so, my red A packet is blocked by head of line blocking and is further delayed, which further delays the red B packet. And then I can continue with other flows and restart the profile. And here, the number at the bottom shows the time spent inside the interleaved regulator. And as you can all see, here we have 0, then 1, 2, 3, 4. So it linearly increases, and we reach unbounded latencies. So our contributions in this paper, first of all, there is a toolbox for modeling redundancy mechanisms in the framework of network calculus in the form of Ravel curves born on the misordering. Also, we analyze the interactions between redundancy mechanisms and interleaved regulator, or if I say it with TSN terms, between FRERE and ATS. And the conclusion is that the interleaved regulator placed immediately after a packet elimination function yields unbounded latencies. And in TSN terms, it says that TSN ATS immediately placed after a TSN FRERE sequence recovery function can yield unbounded latencies. There is a solution that is reordering the packets prior to the regulator. I want to mention this solution is available in .NET because they have what they call the packet ordering function, the consequence of which have been analyzed by Mohamed Pour and Ludovic, but this is not available in .NET as of today. And just to, because I still have 2 minutes more to see the application of this on our industrial use case. This is so my use case, and I'm considering one pass, so between P2 and MC1, in which here I have my packets, here I have the packet replication function, I have my redundancy part here, and my packet elimination function. And as I've discussed, I can obtain a Ravel curve at the output of my packet elimination function, but it can lead to a high latency bound in the switch 1 here. And so I'm considering that perhaps I can place a regulator after the packet elimination function, or an assembly made of a packet ordering function of .NET followed by a regulator. And these are the latency we obtain. So this is a baseline with nothing. If I place a packet elimination function immediately followed by an interleaved regulator or TSN ATS, then I have unbounded latencies. If I place it with a perflow regulator, then I pay a penalty, and we see that we are closer to the deadline. But if I accumulate by doing a packet elimination function, then I reorder my packets to take into account the misordering caused by the redundancy, and then I regulate, then I have decreased the latency bounds. And actually, I decrease the latency bounds of several flows, not only this one, but because all the other flows, we also suffer a smaller contention here. And this is the end of my talk, so I'm happy to get your questions.
We have a small technical problem. We forgot the second microphone.
Oh.
So I think I would ask the presenter to repeat the questions for the Zoom audience.
Okay, so are there any questions first in the room? Yeah.
Yeah, my question may be naive. On slide 16, there was this head of line blocking. What is the reason for that? Is the reason for the head of line blocking that you have a class-based shaping? What causes the head of line blocking?
I don't think it's exactly class-based shaping, but the interleaved regulator, it is not required to process all the flows of the class. It can select some flows. And for example, in TSN, what is typically do is that it will process only the flows coming from one input port. But among all these flows, they are processed in a FIFO manner.
And that causes the head of line because you have somebody before you that has. So wouldn't the solution be to not do that?
To have two different perflow regulators, for example, like in this.
Or do something else. Yeah, there are different ways to implement a regulator.
I would tend to agree. And so the perflow regulator, the initial idea was for one flow, I require one queue. And so I believe that maybe when the interleaved regulator was introduced, it was in an effort to reduce the hardware costs.
Yeah, but if you're using a virtual clock-based shaper that's using kind of a timing wheel or something, then that would work, and you don't need this and would not have this problem. So it means you're not using the. I mean, not you. It's not the correct regulator.
Yeah, I agree with you that the way it is written in TSN ITS for the moment is looking like the interleaved regulator, and it has several issues. Yeah. I haven't.
Sorry, thank you.
Thank you for the talk. I find it really interesting that we have to take care about the interleaved regulator so much, so that could be a problem. And I was wondering about your latest results, where after packet ordering, you said that the result of the interleaved regulator and the flow regulator in the last slide, they look pretty much the same. And my question is whether you have like more test cases which also have this result. So is it? Can you like basically decide arbitrarily whether you use interleaved regulator or the flow regulator, or are there some scenarios in which one is better and the other is better?
Yeah.
Oh,
Which is a challenge because I don't want to say anything stupid, but the question was about the difference between the two and in which cases I would prefer a perflow regulator or an interleaved regulator. So there is a fundamental reason why we have exactly the same latency band. It's because in both cases, we can apply the shaping for free property that says exactly the same. The perflow regulator and the interleaved regulator do not increase the latency bands. And then on the question of when I prefer to use a perflow regulator on an interleaved regulator, the first piece of answer would be cost. Again, there is this notion we are not sure how much perhaps the perflow regulator is require more hardware than the interleaved regulator. And the second one also I would say is that, sorry, I need to go back to the beginning. So the shaping for free here requires this system to be FIFO per flow, whereas this shaping for free requires the system to be, sorry, FIFO per flow here and FIFO only here. And in some cases, and for example, when we try to break cyclic dependencies with traffic regulators, then we have more liberty with the perflow regulator in choosing which previous system we want to reshape, basically.
So maybe we can thank again Ludovic.
Thank you.